We will see what is shown in the screen and how to optimize to the image. At the end, we will review some of the most important post-processing tools in 3D imaging. Medical ultrasound is based on the use of high-frequency sounds between 2 and 15 MHz to aid in the diagnosis and treatment of patients. It gives us real-time images by the reflection of the ultrasound wave in the organ surfaces, whose echoes are captured by the transducer. Here we have two examples of two different ultrasound waves. The orange one has a narrow wavelength and a high frequency as opposed as the blue one, and both are going to have different penetration based on the attenuation coefficient. The attenuation coefficient is a parameter that estimates the decrement of the ultrasound wave in a certain tissue depending on its frequency. So when frequency increases, the attenuation coefficient increases and the penetration decreases. What we have to remember is that penetration is inversely proportional to frequency. There are plenty of probes in the market, and when we are going to choose a probe, we have to think about the penetration we need. And we will choose it tending to its frequency. It's normally shown on the probe, and like for example, RIG 529 or 6-12. When we are performing an ultrasound, what we are looking for is for the best image resolution. On one hand, we have the spatial resolution that has two aspects: the axial resolution, that is the ability to distinguish two objects that are in the same axis of the ultrasound beam. And we also have the lateral resolution, that is the ability to distinguish two objects that are in a plane perpendicular to the ultrasound beam. There are many things that we can adjust to improve spatial resolution. We can increase the frequency and reduce the beam width by focusing. That is going to increase the frame rate, but we can also use a high number of focal zones and increase the lines per frame. But we have to know that this is going to affect the temporal resolution. On the other hand, we have the temporal resolution, that is the frame rate. It is very important when we are looking at moving structures like heart or vessels, and the human eye needs at least that the image is updated 25 times per second. And there are many things that are going to affect temporal resolution, like line density, the number of focal points, as we said, the depth, and the Doppler. The Doppler is going to reduce the frame rate by a half, so it's very important to adjust all the parameters to have the highest frame rate before using Doppler. Now we are going to briefly review the information that we have on the screen. We have this white triangle on the left that it's the point with the best resolution on our image. We have this green signal here that corresponds with the notch on the probe. If we put the notch of the probe to the left, then this side will be the left of the patient. On the right corner, we have the name of the probe, the frame rate and the depth, the angle, the name of the protocol, if we are using harmonics, the gain, the contrast, and the grayscale map, and if we are using any spectral reduction or compound imaging. And here we have the thermal index for soft tissue and bone and the mechanical index. Okay, how to optimize our 2D image? We all have all these protocols depending on what we are looking for, but we can also adjust some basic parameters as those we have here. We can start with the automatic optimization. It's going to analyze our image and give us the best contrast of that image. We have to adjust the angle, that is the beam width, to increase the frame rate, as we said. The depth is very important, that we have to put the region of interest in the center of the screen. And and adjust the focal zone. Focal zone must be in the place we want the maximum resolution. We can also use more than one focal zone, but it's going to decrease the frame rate, so the temporal resolution will be worse. We have the gain control that is going to increase the overall brightness of our image, and the time gain compensation here, that the echoes intensity are going to decrease in depth, so we can adjust it using the time gain compensation. But we have to know that not only the signal is going to be higher, but also the background noise. We have some other parameters, like the dynamic range is the range of the ultrasound amplitude from the smallest to the highest one that the ultrasound machine is going to detect. A high dynamic range will give us a high values of grayscale and a smoother image, while a low dynamic range will give us more contrast image. The tissue harmonics will decrease the artifact. It's based on sending and receiving signals at different frequencies, but sometimes, in difficult cases, using harmonics, the image will just disappear. So in that cases, we should turn off the harmonics to try to see something. We also have the compound image. It combines 3 or more images from different steering angles in one image. Classically, the ultrasound probe sends the ultrasound beam in a plane perpendicular to the head of the probe and then listen. But now the transducer sends different ultrasound signals with different angles and then combine them to reduce artifacts. And finally, the speckle reduction has an algorithm. It detects the weak and strong signals. The weak ones are supposed to be speckled and will be eliminated, and the strong ones will be enhanced. Once we have adjusted all those parameters, we can go for the acquisition. We must put the probe in the center of the region of interest and stand still. We have to adjust the angle and the 3D box and start our acquisition. In a few seconds, we will have the multiplanar view. This is the angle that is going to reflect the depth of the 3D box. And during this scan, like Peter said, the machine is going to take several 2D pictures that will combine to show us the multiplanar view and the render view. We have to take into account when we are doing 3D that the greater the angle, the longer it takes. It's very important when we are studying structures with movement to adjust the angle to the region of interest. And also the image resolution is going to increase the time of acquisition and to decrease the frame rate. It affects temporal resolution. So it's recommended to use mid to high resolution for obstetrics 4D and very high for gynecology. The post-processing, first of all, I will do a quick review of how to navigate in the multiplanar view. And now I will check if you understood, Peter. To do so, we are going to start with the coronal view of the uterus, and then I will rotate it in different planes. If we have the coronal plane of the uterus and we rotate it in the x-axis, the uterus, we will get the axial plane. This is because the uterus will make the same movement as the roast chicken does. If we have the coronal plane and rotate it in the y-axis, we will get the sagittal view, and this is because the uterus will do the same movement as a ballerina in a music box does. Finally, if we have the coronal plane and rotate it in the z axis, the uterus will make the same movement as the hands of the clock. So when we are reconstructing a 3D image, we have to think about how we want our image to move, like a roast chicken, like a ballerina, or like the hands of the clock. If we get lost, we have just to press in it and go back to the beginning. Now I will review the most important post-processing tools. We have the HD Live. Classically, the 3D image was illuminated from the front, so it gives the image to appear flat. But with HD Live, we have a light source that we can move all around the 3D image, and the 3D impression increases. The HD Live silhouette, it enhances the edge of the image. We can adjust brightness and shadows. Vocal, it's mainly used in oncology because we can measure the volume of the lesion at the diagnosis and at follow-up. And in reproduction, we can also use it to measure ovarian volume or to measure the endometrial or subendometrial vascularization. And at the beginning, when we started to use sono-AVC, we also used vocal to delimitate the contour of the ovary before the application of sono-AVC. This is an example of the endometrium volume using vocal. The sono-AVC is a specialized software that automatically depicts the hypochoric structures into a 3D volume of the ovary. It gives us the three diameters, the mean diameter, and the volume of each follicle. And every follicle is color-coded, so it's very easy to identify them on the 3D reconstruction. We have two variants of sono-AVC, the sono-AVC antral and follicle, that we will review in depth later. The multi-slice view or tomographic ultrasound imaging, it allows us the volume dataset is shown as parallel images that we can adjust the separation between the image and the number of images that is going to be shown on the screen. The Omni view allows us to create our own plane of visualizations through the 3D volume. It increases the signal to noise ratio. It gives us a better contrast resolution, and it's also better. It's also very good to demonstrate ill-defined lesions. The VCI, it looks like a multiplanar view, but all of the planes has an increased thickness. The magic cut allows us to eliminate structures that may be in front of the area of interest. And the volume SRI is a filter that is applied to the volume dataset before the sectional plane are presented, and it improves the quality of B and C planes. So in conclusion, 3D ultrasound is a powerful tool to improve the diagnosis and accuracy in gynecology and obstetrics. It requires a learning curve for both the acquisition and the post-processing. 3D image quality depends on 2D, so it is not easier. It depends in our skills with 2D. We all have our own protocols, but we have to be used to adjust the basic parameters as the 2D field, which is the angle, the depth, the focal zone, and the gain. And in difficult cases, remember that there are other parameters that can help, as the density lines, the number of focal zones, the SRI, CRI, and always mind the frame rate. Adjust the parameters to have a good image resolution with the best frame rate possible. Thank you very much.
Thank you, Adela. This was